Okay, hi everyone. Thanks for joining today. Today it's my pleasure to introduce Pietro Perona, who's currently a professor at Caltech in electrical engineering, computation, and neural systems, where he directs the computation and neural systems lab program at Caltech. Pietro Perona is the recipient of the 2013, Longuet-Higgins Prize and the 2010 Kohn-Derenk Prize for fundamental contributions in computer vision. He's also the recipient of the 2003 Institute CVPR Best Paper Award, as well as the 1996 NSF Presidential Young Investigator Award. And today he's going to be talking about some of his recent work on studying how number sense emerges in childhood learning, which I think is a topic that we're all very interested in here. So yeah, with that, I'll hand it over to you.
Wonderful. Thank you, Osbert. And thank you for inviting me. And it's very exciting for me to be talking to people at UPenn. And I've always loved visiting UPenn. And this time it's this way through Zoom, which is sad because I cannot see you directly, but also good because I don't have to spend 2 days on a plane to get there and come back. Okay, so this is, by the way, ask me questions anytime. I cannot monitor the chat, but if Osbert can look at that and stop me if there is a question, I'm happy to stop and clarify. So I typically work in computer vision and machine learning and a bit in perception and modeling visual systems. And this particular project is the result of COVID, where a student of mine, Nihar Kondapaneni, and I, so Nihar started, looking at each other, saying, we cannot go to the lab, what do we do? And Nihar was working on some very interesting experiment with mice, and that couldn't be continued under COVID. And so we came up with this other question that we found quite interesting. And so what's the question? And so first of all, just to motivate you, I want to remind all of us that we know about natural numbers. And so what are natural numbers? And about 120 years ago, mathematicians came up with a definition that satisfied them. And natural numbers are the result of being able to put sets of objects in one-to-one correspondence. And so these one-to-one correspondences between sets induce some partition of all sets. And so the property that is common to the set, to each set of sets is the number of items in the set, right? And so that's a definition. And there are many properties, like the fact that you can order them and operations you can do on them and all of that. And so one day, walking on the beach, I found myself wondering about where numbers had come from. Namely, do humans come up with numbers just when they are born, just because we're humans? Or do we have to be taught? And what was the history of numbers? And I realized I knew nothing of that. And so I started rifling around, and you find things such as this one. So by the way, I don't pretend to give you a whole history, but just to give you a couple of sample points. So this is a very old hyena bone. And so paleoanthropologists believe that these markings are done on purpose and they're not decorative, but they have to do with somehow counting. And one thing I want to point out is that when you count, it doesn't need to be a counting where we know all the properties of the natural numbers immediately. It can be counting exactly in the sense of the definition where we put in one-to-one correspondence two sets, and that's the only thing we know how to do. And so you can imagine here somebody holding this bone in their hand and passing their thumb onto these notches. For example, suppose that there is a big storm and the tribe or the group of humans is out foraging and they have to come back to the cave, and the matriarch is there on the threshold of the cave, and she's putting her finger and counting the people who come back, and then she knows that everybody's back. Or maybe if she doesn't end up with the last notch, she knows that somebody's missing, and so they send out somebody to look for them and so on. So that would be something that you could imagine. So an early version of numbers. And similar reasonings are made about these bulla, which are apparently containers of pebbles that were used for verifying that a certain number of, say, sheep that had gone to the pastures in the summer had come back and so on. So it's always one-to-one correspondence. But as we know, then you can go beyond that, and you can think about ordering again, and you can think about representations, and so having symbols that are associated to the numbers, and which developed more recently, maybe about 4,000 years ago. And so you find a lot of properties, amongst them the abstraction of a property, this idea of counting, addition, so being able to manipulate these symbols, notation, and so on. And some people feel that then it's obvious that numbers have to do with language, because language is our system of symbols that abstract properties, etc., etc., and we can manipulate them and so on. Now, this, though, is not a complete picture, because psychologists have noted that there are also perceptual properties associated to numbers. And here, with this picture, I want to illustrate two. So if I ask Osbert to tell me how many birds do you see, Osbert, as quickly as you can?
6.
Okay, so Osbert had to pause for about 1 second. So it means that he counted them. And so I'm now asking, I don't know, Hu Jiahuang to tell me how many buffalo she sees. Well, one. Okay, so she didn't have to pause very much. So the subitization is the ability of your visual system to tell you how many of something there are. And it works only if you are up to 5, so not more than 5. So up to 5, you're exact, and you can do it without thinking. It's immediate. And beyond that, and so the 6 birds that Osbert saw, well, he had to count them to tell me the number. Now, there is another property that your visual system has, which is numerosity estimation. And so numerosity is the property of how many there are. And so if I ask Osbert now, I'll show you another picture, Osbert, and you have to tell me quickly, without counting, how many. You know, how many?
15.
Okay, 15, great. So Osbert came, so he may be right on the mark. I don't know if somebody wants to count and then let us know, but we can get to within 10 or 15% of the actual number just at a glance, like this, for numbers that are fairly large, like 100 or 200, something quite large. So this is called numerosity estimation, which is we estimate the actual number of items, not just the amount of pixels that are taken up by the objects or anything like that. It's really the number. And so these are two properties that are connected to the natural numbers or into quantities and are perceptual. And it turns out that there's this historical curiosity. Somebody called Jevons, who is apparently the father of mathematical economics, one day was probably not too busy, and he realized that he could count at a glance. And so he tested himself by making little pellets of paper, I think, or maybe grains of rice on a piece of black velvet. And this is the table that he compiled. You know, the actual numbers are the columns and the estimated numbers are the rows. And you can see that up to 5, he was getting them more or less all correct, with maybe 3, 4, 5% error. And then beyond that, things are much more qualitative. And so this is in a table, subitization and numerosity estimation. Now, psychologists have become recently interested in these properties of a visual system. And a question that of course comes up is, again, do we do numerosity estimation because of some logic property in which we identify the objects and somehow we combine them with operations across the visual field? Or is it a much more, in quote, perceptual, intuitive, mechanistic thing where there is no symbol being manipulated? And this would be the divided line between thinking that numbers have only to do with language or that there is something more to them. And there is a very nice experiment by David Burr and John Ross, which nails this by using a technique which is called habituation. And those of you who study psychology know what I'm talking about. So if you look at the bottom right of the screen, you can fixate on the cross, and somebody could tell you, are there more dots on the left or on the right? And it's quite intuitive that you would get it right most of the times. Now, if you want to see a curve of that, you see it on the left. Look at the curve with the white squares. And so there is a probe at 30, which means that one of the two sides is 30 objects. And the question is, as a function of the other side, how often do you say that the other side has more dots than the probe side? And you see that this curve, which is called the psychometric curve, has a certain slope, which is quite steep. And so between 20 and say 40 objects, there is a little bit of an error rate. And apart from that, then you're more or less nailing it, right? And so you do flip at about 30. And that shows you that you have this plus or minus 15% error rate, and overall you're very good at doing it. Now the cute thing is, if somebody adapts you to a pattern of dots, and so suppose that you first fixate to the pattern on the pattern above, and then the pattern below is presented to you, it turns out that the whole curve shifts over by a lot, and you see the black dot curve. So it's not a subtle effect at all. Somebody can make you switch at 100 instead of at 30. And so here what was being habituated was the side that is being tested, not the probe. And so what this means is that the circuits in the brain that are estimating are probably very much of the qualitative psychology side, of the kind that the brain adapts. And adapting is sort of a form of gain control, because your visual system needs to be calibrated all the time in order to give you the right answers. And so even numerosity estimation needs to be calibrated by itself. And I hope that this point is clear. I don't want to belabor it because it's not the point of my talk. It's just to say that there is strong evidence that numbers are highly coupled with circuits that carry out perception. So a question that you might ask is then, are the numbers due to language or are they due to perception? Okay, and probably the right answer is in between, but we're curious to see how far could we push on that. And another question is, are the natural numbers innate? Are we born with them, or do we develop them as our brain matures? Or do we have to be taught by a teacher in kindergarten to start counting on our fingers, and et cetera, right? So these are two questions we can ask. Now, this question had been around for a while, it turns out, unbeknownst to me, but as soon as you start getting into a new field, you discover a wealth of things that are quite interesting. And so there is a very nice paper by two people at the University of Padua, which happens to be my alma mater, Stoyanov and Zorzi. And they had an idea which was very simple. So take a deep network and arrange it as an autoencoder, where you are taking in an image and you pass it through a bottleneck, hidden layer 2. And then there is a mirror image version of this network, which I'm not showing here, which decodes the image and tries to reproduce exactly the same image with which you started. Okay, so that's very simple exercise. And something like this happens. So the inputs are the small squares and the outputs are the large ones. And you see that the network is able somehow to reproduce some aspects, at least, of the inputs. I hope that this is clear at the moment. And what then Stoyanov and Zorzi found is that in the hidden layer, namely the bottleneck of this autoencoder, then there are some units that are forced to in some way encode for the essence of what goes on. And these units seem to be tuned to numerosity. And so you see one, so this is a sort of a summary of population activity. And so if the brain had access to something like this, it could estimate numerosity, okay? So the idea here is that you could self-train at least part of the system, namely the part that encodes for the information. And then, of course, if you have a signal lost somewhere in your brain that is correlated with numerosity, you've got to have some supervisory input in order to be able to connect this particular signal with the answer you want to give, right? So, but this was inspiring. So it's not unsupervised learning. You still need a teacher, but the teacher has an easier job because you already have the right representations in your head. It's just a matter of connecting the representations with the desired output. I want to show you another paper that came out in 2019. And this one is also surprising to some extent. And so they take one of these deep networks, and so take a ResNet or equivalent, and they train it to classify the ImageNet data set. And so I'm going fast on these things because imagine that a deep network and ImageNet are words that most people have heard by now. So this network does a good job classifying these pictures. And now what you can do is, I don't know if you see my mouse, you can look at some intermediate layer of this network, and I forget which one they look at. I think number 4, but I could be mistaken. And you can see what the tuning of the mechanisms in that layer is to images that the network has not seen before and that contain a number of blobs, as you can see here. And the blobs could have different shapes and different sizes, and they are in a random position. And so what they find is that they do find units, again, in the sleep network that are tuned to again, the number of objects, give or take. It's a very broad tuning. It's a bit, washed out, but you can imagine that now if you had supervision, you don't need much supervision to discover these units inside your brain and use them for numerosity estimation. So there, again, there's a suggestion that numerosity estimation, at least, may be the result of a lot of unsupervised work that your brain is doing, and then a little bit of supervision. And so we thought
I'm just wondering, so because you could, like, for these examples, the number of objects is kind of very closely related to the area of white objects. And is that something, do these results show specifically that it's able to count the number of objects and it's not just measuring the...
Yes, they have controls. As you can see, for example, in the middle row, the few dots are big and the many dots are small to control for area.
I see.
Et cetera, et cetera. So they did their best, let's say. But it's a very good point, and you should keep it in mind because what I'm going to tell you about has to be tested the same way. And so we have to remember that this is a possible confound that we need to be careful about.
Okay, thanks.
Okay, so we thought that we wanted to push the envelope in 2 or 3 different directions. So one is, can we conceivably come up with a system that is completely unsupervised? That's one. And the second one is, completely unsupervised is never completely possible, but let's say even less supervision down to n equals 1 or something like that. And then can we find a theory that tells us about not only numerosity estimation, but also subitization? And can we find a theory that will tell us about how do these abstract quantities like natural numbers can come up in your brain? And so I took inspiration from this picture of my son when, many years ago when he was an eighth of the size he's now. And here he was playing with little shells on the beach. And so in between his legs, he would put shells that he was interested in, and he would pull some out and put some in and so on. And so here I want to more or less reproduce with tomatoes from my garden what I think he was doing. And so children, when they are about 1.5, they learn this pincer motion in which they can grab an object at a time, and they play a lot with little objects. And those of you who have children or have had children of more or less this age remember it. And so this is the game. And so sometimes you put one in, sometimes you pull one out, sometimes you scramble them a bit, et cetera, et cetera. And you keep looking very intently at what you're doing. It's quite remarkable how absorbed they can be in this kind of game. So to make this into something that we can treat mathematically, I'm abstracting away a little bit, and so I'm allowing 3 possible actions: a take action where I take one object away, a put action where I put one object in, and then a shake action where I move things around. Okay, so the question is whether we can, by playing around, we can reach an abstraction where we form categories in our head. And I purposely scrambled, use letters instead of numbers that are a little bit scrambled because it's unclear initially what the categories refer to, but they are categories that group scenes that are very different one from the other, but identical in one respect, which is the number of objects in them. And so can we develop this representation, and then later can we put these categories into a relationship where we know which ones are bigger, which ones are smaller, and so on. Okay, so that's the idea. So again, we start from assuming that someone has learned to pick up one object at a time and drop it at will in some place, and that they're interested in playing with it. So these are two assumptions we're making. And so here play is, again, an assumption, and we want to see what happens. So, so the idea would be that, again, through some perceptual steps, an image gets mapped into an embedding inside your brain. And the embedding is similar or the same for images that contain the same number of objects and different for different objects, so that we can then associate symbols to these abstractions in some way. So how would we do this? And so, of course, in some sense, we want to use supervised learning. The supervision is coming from what? And so the question, so supervised learning, we have a signal and we have a label like your mouse in green that we want to reproduce, and we compare the output to the input and see if they correspond, and if they don't, we adjust some parameters of the embedding or the classifier, right? So the idea would be that in some ways we could learn an embedding that produces these numbers. However, that's precisely what we don't have. We're assuming that the child who is playing has no notion of the numbers. They can only pick up objects and drop them. And so this is not going to go very far. And so what the child knows is which action they're taking. And so maybe we can go with classification of the action that is being taken. And maybe that will do what we want. But of course, as you can see, this is not, again, feasible, because when I look at this image, I have no idea which action I've taken because I don't know what comes before or what will follow it. So this is not also good. And so our point of view is that you have to have some short-term memory that allows you to analyze one image and what follows, and then classify the action that took the first image to the second image. And so training this network, which is called the Siamese network in the jargon of deep network people, because the two deep networks that you see in time are actually the same network operating at different times, then this maybe is a good approach. And just to have a different representation that maybe is clearer. So here we go from vertical to horizontal, I'm sorry. And so you have the image or the scene at time t and t+1 at the bottom. And then you perform an action, which in this case, it's a take. You've taken a ball away. And in doing so, you've also perturbed somehow the order of the balls. And each scene is analyzed by perception, which is symbolized by this pair of eyeglasses. And a certain representation, which is abstract in your brain, is created, zt+1. And then these two representations are compared by a classifier that tries to guess that the action was take. And now you can have supervised learning because the predicted action is compared to the action that is performed. And now this is a clarification I want to make. So this is supervised inside the head of the child because action is teaching perception, but it's unsupervised if you see the child as a system who is just playing around, right? Okay, so now the way we implement it is in a very mild way. So we have feature extraction is done by a CNN, followed by some fully connected layer that generates the representation ZT. And then there is another fully connected network with, I think, 2 or 3 layers that compares it to Z and produces either one of put, take, or shake. I hope that this setup is clear. To make things easy, we use synthetic images, and we have two ways of generating them. One is each dot corresponds to an object, and the dots are all the same size and contrast, and they can be in random locations. And so that's the one you see above. Or each dot can have a random size and contrast within certain limits to generate sequence that you see below. And some contrasts are very low. So the bottom right picture contains 2 dots. I don't know if you see them on your screen or not, but that's okay. So Osbert tells me yes. Okay, so let's suppose we train our network using this technique. What do we expect to see? And we have 2 places to look at. One is what's the performance of a predictor, and then what is the representation that is coming up. Okay, and so here is the performance of the predictor, or the classifier. So it turns out that we carried out this experiment a number of times, and here you see what happens when you carry out with 3 objects. So the child, metaphorical because there was no child really there, is either seeing 1 object or 2 or 0 objects, 1, 2, or 3, but not 4. And so you can only put and take so that the objects remain between 0 and 3. And as you can see, after a bit of training, the error rate is around 1% for all 3 actions, take, shake, and put, up to 3 objects. And as any one of you who has used machine learning and deep networks in particular knows, generalization outside the envelope within which we trained is not very good. And so you see that the classification of the actions for 4, 5, 6, 7, 8 objects goes up to chance level very quickly. Chance level is 30%. Okay. So again, learning is excellent within the limits of the set of objects that the system has seen, but not beyond. And so here you see what happens if you train with 5 or 8 objects, and we see that there is more generalization when you train with 5 and 8 objects than with 3. And another thing that is interesting is what is the behavior of the error rate within the number of objects in which a system was trained as a function of the dimension of the embedding. And so here we had our first surprise, namely the dimension of embedding does not matter. You can go from dimension 1 to dimension 256, and the error rate is constant as far as we can tell, so about 1%. Okay, any questions here? So here again, we have a system that was trained by watching sequences of scenes with blobs in them, and given a pair of scenes with 3 blobs and then 2 blobs, the system has to guess take. That's what it has to guess. And the system has 2 stages. One is the perception, which produces an embedding, and then classification, which decides which move was made. And it turns out that what we see is that the embedding can be anything between 256 and 1, and things go fine. Okay.
So just to make sure, so you're saying you can represent the entire image using just a single real number, and that's
single real number. Yeah, okay. A single 1 dimension, which starts giving you some idea of what's going to happen. So up to now, we know that the network can be trained to predict an action, and it's accurate when the number of test objects is in the same envelope as the number of training objects. The error goes up for more, and the dimension of embedding is irrelevant. So this now moves our attention to the embedding itself. And now we want to know what is there in the embedding. And so what I will show you is pictures of the embedding when the embedding is 2-dimensional, because now I can represent it on a piece of paper, on a slide. And this is what I see. So you see some dots which are grouped in a certain region of the plane. And the dots are colored by the number of objects that so the dots are the embedding of a given picture, and the number of objects determines the color of the picture. Notice that here Nihar didn't stay within the bounds of 0 to 3, but he went to 30, so 10 times more than the number of objects that we use for training. And you notice a number of interesting regularities here. First of all, indeed, the set of points is on a 1-dimensional manifold, give or take, a little bit fuzzy, but say 1-dimensional. So that's a first surprise. usually when you train embeddings, then they take up all the space that is available. But here, that's not the case. Now, the second thing you notice is that the dots on the line become darker from one end to the other, indicating that somehow we have an ordering of the images based on the number of objects in the images. And now another thing you notice is I enlarged the top right portion, and you see that there are some islands somehow. So while the line in the blue part of the line is a continuum, the lighter colored part of the line, yellow-blue, is divided up into islands. And so you wonder what those islands represent. And so what we did is we looked at, we colored specifically the dots according to the number of objects, or in fact, we did something different. So we did some clustering, unsupervised clustering of those, of all the points. And so you see that we found some clusters. One is a big brown cluster, and then there are some small clusters that are colorful on the top right. And so we name them with random labels, but it turns out that those labels correspond indeed to the natural numbers. And so the labels are now on the rows of this matrix, and the number of objects is on the columns. And you see that the first few natural numbers are grouped in a perfectly clean way within the first few islands. And then around 5, they start spilling out. And then beyond 7, it's all one thing, it's many. So it's as if the network has discovered the concepts of 0, 1, 2, 3, 4, 5, 6, many. Okay, so this is yes.
So it seems like this embedding is able to generalize in terms of the number of objects, but the prediction layer on top of this embedding is not able to.
Okay, generalize in terms.
So this embedding, this embedding looks like it's actually able to capture the ordinal numbers up to 30 quite well in a semantically coherent ordering, but the put, take, and shake logic, if you will,
yes,
on top of this embedding is not generalizing.
That's right. And so my interpretation here, so thank you for that comment, Isong. And so for me, so this is an interesting point, which is if we look at a system in the usual, under the usual, how did my supervised learning do? It's not surprising. It's just interpolating data that we saw before. And yet it's developing under the hood a representation which far exceeds the bounds of what it was trained. And it's there waiting to be discovered in some ways.
So I could just, I mean, just as a thought experiment, I don't mean to derail your talk. Just as a quick thought experiment, I could just write down a rule-based classifier for put, take, and shake based off a one-dimensional linear dynamical system or linear system, right? I could just write it by hand after looking at this embedding, and it would generalize.
Yes.
Okay.
Yes.
Well, I guess it does look like the representation is a little fuzzy, so I don't know if that causes problems.
Yeah, so we've looked a little bit at what the fuzz means, and now I don't remember. It's things like how centered the points are, things like that. You know, if you move across the line, you know, what these points mean, and so on. So I'm coming close to answering that question in a little bit towards the end of my talk. Okay, so let me skip this. Okay, so a question is whether this coloring can support quantity estimation, as you might imagine. And indeed, you can test it in two ways. One is absolute, namely, is the distance from the origin. So you can think that somebody could calibrate the system by taking the distance between 0 and 1 along that line, and then use that as a yardstick. And how would they estimate all the rest of the numbers, or the rest of the quantities? And you see it here. And so the light blue line with violin plots is how the system is able to do, how well the system is able to do, namely with 20 points, and you see it here, it will estimate 17 plus or minus 2. Okay, I don't know if you see this violin plot. And at 15, it will estimate 14 plus or minus 2, etc., etc. Okay, so it's slightly underestimating, but it's not doing a bad job at all. And the other lines you see are lines obtained from human subjects that we compare to the system. And you see that human subjects, and the red line would be perfect performance. So human subjects are in that green zone that you see, and so they also a little bit underestimate. And the system is, if at all, more accurate than the human subjects. This doesn't mean anything, of course, because that we train it in a way that doesn't mean is not exactly how human subjects are trained, but you get a qualitative idea. Now on the right, we did a relative numerosity estimation test, like the one of Burr and Ross, where we used our own displays, which you see down in the bottom row. And again, you see one of those sigmoids, and it's a little bit better than human subjects again. Okay, and so human is green and our system is blue, the blue model line. Okay, now we go back to Osbert's question. And so you could worry here that if you compare 12 and 20, well, the number of pixels that are non-black is very different. And so maybe the system is purely looking at how many black pixels there are, how many white pixels there are not, it's not counting. And so we can take advantage of one quirk of how we generated our data, which is we have these random sizes and contrast levels for our dots. And so we can identify in our sequences of dots that samples that by chance had lots of small dots or lots of big dots or lots of bright dots or lots of, and so we can try to separate out the effects. And so this is what we do here. And so in the first row, what you see is a sequence where the numerosity is increasing from 14, 16, 18, and the total number of brightness is going down. So here is encounter tendency. The brightness is encounter tendency with respect to the numerosity. The second one is the area of pixels that are non-black. And the last one is the convex hull of the size of a convex hull of these points. And so you can always find, it's not frequent, but you can always find samples that go against numerosity. And the question is, does any one of these other variations predict a performance? And it turns out, no. So you see lots of flat lines here, meaning none of the potential confounds that we thought of was correlating with numerosity. Okay. Now I'm really at the end of my talk, so that we leave some time for Q&A. So what predictions can we make? And so one obvious prediction is that if a child grows up without hands, or they have motor difficulties, then they shouldn't be able to learn about natural numbers, or they should learn the natural numbers with some retardation, because of course you have other sources of information, not only your own manipulation. You can make sounds using your feet, or you can watch TV and maybe somebody's moving the objects for you, etc., etc. But you know that would not be as efficient. And we found indeed one paper that seems to show something like this, and you see the main pictures here, where and so now I'm blanking out on the age of these children, but there is some motor some coordination problems some kids have. And so here they show that on a certain test, which is again comparing the ratio of comparing two displays of numbers, and so that with it perceptual, it has nothing to do with motor, and yet you see that the blue points are above the red points. The red points are the children with a dysfunction, and the blue points are normal children. And so it looks like there is an effect in these children. Okay, so I want to stop here to leave some space for hearing your questions and discussing the points. Okay, so one is that we find that this number sense can be learned without an external teacher. And so the secret to it is that manipulation, which is learned before, can teach perception, and then perception will develop the suitable representations, which include separate classes for the first few natural numbers, and then a number line that allows you to estimate quantities, and then the perceptual properties of numerosity and subitization. And so all of this happening in the same model. And we're also intrigued by the fact that we found here a situation where machine learning is appearing to extrapolate, and so to develop abstractions and representations way outside that are effective or useful, way outside the domain within which the system was trained. So again, I want to show a picture of Nihar here, and I'm happy to hear questions. Thank you.
Thanks so much for the really interesting talk. So yeah, I guess we can open the floor to questions.
Can I ask the first question?
Yeah, go ahead.
Thank you.
Yes.
Yes.
Thank you very much. Thanks a lot for the talk. I was wondering about some kind of a comparison to, say, contrastive learning. So from what I understood, you have two Siamese networks that are taking two sequences of an image that is somehow perturbed, and the output of the network is trying to predict the type of perturbation, right? The action that caused to go from xt to xt plus 1. So what I'm wondering is that, is it possible for us to directly apply contrastive learning? So just like, minimize the contrastive loss instead of performing the prediction and sort of comparing the representations of that kind of a network versus the current network.
Right. So yeah, I think it's yeah, we haven't tried, first of all, so I don't know, but it's my intuition is that it would work. The reason why we set it up this way is because we wanted to think about how a robot or a child might do it. And so you have to think about what does the teacher know? And so the teacher here is the motor system. And the motor system doesn't know about numbers. It just knows how to pick up objects and drop them. So if you wanted to train it with contrastive learning, you would have to imagine what's mechanism that doesn't quite know about numbers yet, you would engage for achieving the same goal. And yeah, thank you.
That's right. Okay. Thank you.
Yeah, so I had a question about, I guess, maybe the broader implications of this work for neural networks, because I mean, it seems like, this really suggests that neural networks are learning symbolic structure just from this kind of limited amount of supervision. So do you think that, and I think there is a broader debate in the ML community about whether to learn symbolic structure, whether neural networks are enough, or if we need to incorporate additional structure like logical reasoning into neural networks. So do you think, or have you thought about whether these kinds of ideas might apply more broadly to other kinds of logical or symbolic reasoning? Do you think neural networks can represent?
Yeah, so yeah, I'm pushing my student to think about other ways of other applications, exactly as you say. Now, it turns out that Nihar in this moment is interested in another problem, so we're making very minimal. We have not even published this paper properly because we got distracted by something else. But yes, I agree with you. So here, maybe I don't know if I said it clear enough. So you have an embedding, and it's conceivable that, so one of the steps in our model is that the brain has a knee-jerk reaction to representations where it tries to cluster things to see if it's helping. And so here it's clustering that reveals these abstract quantities. And so the transition between a continuum of situation, which is these tomatoes that could be anywhere on a plate, and the discrete notions of the first few natural numbers, that transition seems to be done by grouping, at least in our model. And so you have to imagine that grouping or unsupervised clustering is always there trying to do its job, sort of a knee-jerk reaction of the system. And so that would be the way in which this particular line of reasoning proposes that neural networks could go from a continuum to discrete abstract categories.
I see. Thanks. Actually, I did also have a follow-up question on this image. So this image was produced for manipulations with just 2 to 3 objects, right? Did you try to see what it looks like if you give it manipulations for like up to 20 objects to see? Like, I could imagine that maybe it'll learn better discrete like clusters if you give it more.
Yes. So So we've tried up to, I think, either 8 or 12, I forget. And indeed, you find more islands, you find more categories. Now, the reason why I showed this particular one is that we were for the longest time working with 6 objects, I think, and finding all of these properties. And so one day we decided, okay, let's try with 3 and let's see if it breaks down. And we still found this discretization. So for me, it was funny to see that with such few objects, so even the number of natural numbers is extrapolated, or it's exceeding the total number of objects that the system could see. So you cannot possibly say that it's just learning by rote that there are 5 numbers.
Right.
No, there are 3 objects total, 0 to 3, and yet it goes up to 6. So yeah, but the larger the number, the more islands you find.
Yeah, I had a question.
Hi, Charles.
First time. Hi. Really interesting work. I guess one way to like summarize this is that numerosity is like an emergent property of certain types of learning behavior. And I guess the question that I had is like, did you try other experiments that didn't work? And like you don't sort of observe this this embedding coming out? And if so, like what were they? Because I feel like that might also give us some sense of what
Yes,
why
yes.
this.
Okay, so this is a very good question, and I need to think for a moment to remember what we did, because inevitably we tried out different things, and why did we settle on these ones? So I thought that so at some point we had also. So first of all, we never tried with real objects like the tomatoes. And so in my mind, this should work if you play with tomatoes or acorns or anything. And so we didn't. Now, one thing I think that one thing we decided to do was that even in the pick and place the put operation, that the objects can be scrambled. And I'm trying to remember, if you don't scramble them, does the system overfit and it's not able to learn a good representation? And that I'm not
I think that would be really interesting if like you don't scramble and maybe it doesn't generalize as well. Like you don't get this nice embedding and it also doesn't generalize or something.
So
that could be
remember that it learns less well. I know how less well, I don't remember. And so, yeah, your question makes me think that maybe if we publish a paper, we should show these other, variants.
Yeah, and I guess another possible experiment is instead of testing groups that are off by 1, if you vary the differing sizes and you just check for greater than or less than or equal to.
Right.
There, you could still, I guess, like this is sort of learning the successor function on integers in some sense. And so you might naturally expect like embedding along a one-dimensional line, but maybe wackier things happen if you ask it to just compare relative counts. Do you still
Charles,
get?
I want to understand what you just said. So what's the experiment you propose, that more objects than 1 are being picked out or put in?
Yes, exactly. So instead of training on, it does.
We tried. Yeah, that works. Yeah, so Nihar was telling me about this just yesterday, so I happen to remember. We had an undergrad working with us during the summer and trying out a number of control experiments. That seems to work. And I think it was going up to, okay, I'm going by memory, maybe 10 objects so you couldn't possibly take away more than 9, but it was taking away a random number or putting in a random number, and it still learns the same embedding. So something I should say is that you see this line structure always in the experiments, but sometimes it's not straight, sometimes it's curved or it has a kink. And that's maybe 10% of the time. So 90% of the times you get a straight line, and 10% of the time it's crooked. And if it's crooked, what happens then? The estimate of numerosity becomes less accurate. And maybe, in my mind, maybe that explains why some human subjects are not very good. Like in the
what
in
is
the
what is the put take, and what are the put take and shake classifiers? Are they 2-layer neural net? Like, do you remember roughly how complicated they were?
Yeah, so there are either 2 or 3 hidden layers networks, and if we did that, it means that probably we saw that linear classifiers wouldn't work, which doesn't make sense because, if all the
one of
points
the
are
things, one of the things we do in my group, Pietro, is we try to do distillation. So maybe it doesn't work because in the beginning it's too unstructured, but then partway through training, we simplify the things that we believe can be simplified. So one thing you
Yes.
could here is you could just throw away the put and take and retrain with a linear classifier.
Yes.
Somehow as an algorithmic, I know we can go into the mathematical reasons why that might work well, but you know, that as a general rule, that tends to work well for us. And I would have to imagine that if I throw out the put and take at this point and retrain with a linear put and take, it would work.
Yes, absolutely. I agree.
Yeah, I had one more question, I guess. Just, I think you mentioned that you had tried some different tasks, but I'm wondering, so I mean, one natural kind of question here is that this, like you chose, this is a specific task that you might imagine children are playing, but you know, there's kind of a very rich space of things that children do when they play, right? So have you considered other kinds of more complex tasks to see if it, like I think one thing is are these like pick and place environments from OpenAI Gym, or like more, do you think that the same kinds of properties would emerge under these more complex tasks, or
Yeah, I haven't
other
thought
kinds
of
tasks you consider?
any other. So yeah, so we started off from thinking about the endpoint, namely about numbers, and we thought of this child playing. I haven't thought the opposite way. And you start with play, and so say, okay, what is this game supposed to generate in your representations? And so that would be an interesting exercise. And we should think, you look at, 3 or 4 activities that little kids do, and you say, well, what if they're just trying to predict how things will look after they do an action? What will they teach them? And so something they enjoy doing is twirling around strings and looking at the loops. So what kind of embedding does that produce? That would be an interesting open, a fishing expedition. What do you see once you look at the embedding? Yeah, thank you. By the way, so something I should emphasize is that probably you guys have thought about, but so when I say objects and counting and so on, of course there are limits even to the human ability. So if you take your shoelaces and you bunch them up, it's very difficult to tell that it's 2 shoelaces or 3 or 1. So the objects have to be fairly contained and not intersect over each other too much, right? They have to be distinct in the visual field.
I had a quick question, kind of following up on Osbert's point about maybe other experiments to do.
Hi, Joy. Yes.
Hey, I'm just curious if you've had the chance to talk with any developmental psychologists that study numbers. So you had a slide earlier about like whether or not some number sense is innate. And I know that, say, Susan Carey at Harvard has spent like an enormous amount of her career investigating that question. So has Liz Spelke and a number of other people. Yeah. And I think they've probably kind of mapped out the space really well on what kind of simple behavioral experiments you would throw at a kid to tease apart these ideas.
Yes, so Liz Spelke maybe has the first papers on this, and I'm going to see her in about 10 days. And so I'm curious to see what she says. In looking at, so they claimed, or they found a certain level of innate perception of numerosity, but it was extremely blunt. So, if an adult has an error of plus or minus 15%, I think that a baby has an error of plus or minus 70% or something humongous, but you see a little bit of a signal. Now, one thing, by reading her papers, I could not understand the difference between novelty versus different number. And so that's something I want to ask her about. You know, how does she know that it's not just novelty? Because we know that babies of a certain age are sensitive to novelty. So what is it that makes her think that it's number and not novelty? So that's the part. So that, yeah, there seems to be a little bit, but not much. So it's difficult to claim that you have these categories in mind already when you are a baby. Now, there are also studies about tribes in the Amazon, how many names do they have for numbers, and some of them have like 0, 1, 2, and then many, and some go up to 4 and then many. And so that was it's also an interesting literature. Of course, you know, that you have to rely on one study that was done by one team going in, and that's it. And so the main these people could do numerosity estimation as well as you and I, apparently, even if they didn't have name for 20 and 30 and so on, but in comparing to displays, they could. The only difference was that the next day, if you ask them how many objects did you see, well, they don't have a name for them, and so they had very faint memories of what you had showed them. Well, if you and I say, oh, it's 20 or 23, then we remember what we said. And so the next day we can recall that. It's unclear that if we recall the feeling we had when we looked at the display, but certainly we can recall how many did we claim that we saw. And these people in the Amazon couldn't. So that was the main difference.
Okay. Yeah, I think we're at time. So yeah, thanks again for joining us. It was really
Thank you for inviting me, Osbert. This was fun. Very nice questions. And I'm happy that Isong was here. When I see Isong, since he's a friend, I know that I'm protected, because if I don't know the answer to some machine learning question, he will. Okay, thank you guys. Thanks a lot.
Thanks so much. And I'll see you all. Bye.